Hello, guys. Um, this is AI Hitchhiker here once again. We are continuing our series on deep dive into the book AI Engineering by Chip Huyen. And today we want to continue our reading and putting down some wonderful notes in the Notion page that we open to put out our notes. So if you are joining live or if you're watching the recording later, welcome. I hope you've got yourself the book. I've put the link to the book in the description somewhere. Um, so get yourself the book so that you don't just become a spectator. You can follow us along. So we are looking at the last time. One of the major things that we're looking at before we close the live was looking at um, the concept of ML engineering versus AI engineering, where we said that traditionally ML engineering is where engineers build foundation models from scratch. And AI engineering is seen as where um, engineers pick these foundation models and build apps on top of it. So technically, an ML engineer will do both. Will be able to build foundation models and build apps on top of the model. Okay, so that is what the book says, sort of separates the two, the difference between a machine learning engineer and an artificial intelligence engineer. And we talked about the three main reasons for the upsurge in AI engineering. First one being general purpose AI capabilities, the fact that AI has moved from just LLMs, or the fact that the foundation models upon which AI applications are built have moved from just LLMs, large language models, to LMMs, large multimodal models. And multimodal models are models that have been trained not only on text, but on different other types of data. So we have images, video, audio, you name it. So if you think about it, when ChatGPT was launched with its very basic models, even at that time, it was called a large language model because it was trained on millions of data, corpus, test. But now that number, even though it was in the millions, it cannot be called a large language model by that standard. And so large language model, that's one of the things that Chip addressed in the book, that the term large language models is even a missing target, because what you consider as a large language model after a year, or not even a year, 3 months, 6 months, that doesn't qualify to be a large language model anymore. But the GPT models that power ChatGPT, and the cloud models that power the foundation models from Anthropic and Mistral AI with their own models, and the Gemini model from Google, all of those big companies that are coming out with foundation models, for most of them, they started with a very basic text generation model, especially ChatGPT when it started. It was just test completion job. So uh, it was configured to be more probabilistic in its response instead of being deterministic. So it was great at doing creative stuff. So people became poets overnight, and it was because that is how the model was trained. Now, it has moved from just being able to complete test, from just generative text to being able to generate images and generate um, other very complex. I mean, it's not just images. You can now generate infographics, a whole lot of things that at first it wasn't able to do. It can even do complex math. And with all of these mathematical and scientific symbols, it can understand it and generate them. It wasn't able to do so at the very beginning. So that is what we mean by multimodal. It's got multimodal capabilities. And that means people can pick these foundation models, you know, make an API call to these foundation models. And now we have MCP. That is like the API um, equivalent for, API became popular because of software. Now MCP will be like the API equivalent for these machine learning models. So its multimodal capabilities have made AI engineering very popular because people are building on it. And there has been an increase in investment in AI. Anything AI, investors are curious and interested in it. And S&P 500 companies that mention AI in their earning call from 2018 to 2023 saw an increase in their stock prices from an average of 4.6% compared to 2.4% for companies that did not. That is one of the statistics that I took from the book, that from 2018 to 2013, S&P 500 companies, Standard and Poor's, that index fund of the 500 biggest companies, I believe in the US, most of them are tech companies. Once they mention AI or anything related to AI in their earning call, people become interested, and there was on average 4.6% increase in their stock prices as a result of that, compared to companies that did not. Okay, so again, that has made AI engineering very, very popular because of that. Then there is this low barrier to entry in building AI applications on top of these wonderful, wonderful models that are being built by the likes of OpenAI, Anthropic, Mistral, and big tech companies, the Googles and the Meta and the Apples and AWS of this world. Okay, so that is where we got to, and we started also looking at some AI use cases. There is a website that was mentioned in the book. There is an AI for that.com, and I checked that website and I got an AI video editor. I've tried it, not to my you know to my taste, but it's good. It did quite a good job, especially with the way it did the zoom cuts was good. The only thing was that um my talking was not syncing well with the subtitles that was coming underneath, and it was a bit jerky. The flow of the video was a bit jerky, but I believe that if this company persists and they keep improving their model, by getting updates and feedback from the users, they can make it better. If they don't only think about making money in the short term, but making it better, I think they can do something well. So today I'm going to continue with the AI use cases, and we are going to start with workflow automation, which is one of the things that I believe is powerful when it comes to the use of AI. Okay, so let's make it mm, right. So workflow automation. Ultimately, AI should automate as much as possible. For end users, automation can help with boring daily tasks like booking restaurants, requesting refunds, planning trips, and filling out forms. For enterprises, AI can automate repetitive tasks such as lead management, invoicing, reimbursements, managing customer requests, data entry, and so on. One especially exciting use case is using AI models to synthesize data, which can then be used to improve the models themselves. You can use AI to create labels for your data, looping in humans to improve the labels. We discussed data synthesis in Chapter 8. Access to external tools is required to accomplish many tasks. To book a restaurant, an application might need permission to open a search engine to look up the restaurant's number, use your phone to make calls, and add appointments to your calendar. AIs can plan and use to AIs that can plan and use tools are called agents. So now we've heard of the term agentic AI, and it's one of the things that has also made AI engineering popular because you need to engineer, you need to build this on top of foundation models. Okay, so connecting AI models to tools is what agentic AI is about. The level of interest around agents borders on obsession, but it's not entirely unwarranted. AI agents have the potential to make every person vastly more productive and generate vastly more economic value. Agents are a central topic in chapter 6. Right. Planning AI applications. Okay. Given the seemingly limitless potential of AI, it's tempting to jump into building applications if you just want to learn and have fun. Just jump right in. Building is one of the best ways to learn. In the early days of foundation models, several heads of AI, um, several heads of AI told me that they encourage their teams to experiment with AI applications to upskill themselves. However, if you are doing this for a living, it might be worthwhile to take a step back and consider why you are building this and how you should go about it. It's easy to build a cool demo with foundation models. It's hard to create a profitable product. Yeah, that's true. So this is very important. Planning, knowing why you want to build an AI application. So use a case evaluation. The first question to ask is why you want to build this application. Like many business decisions, building an AI application is often a response to risks and opportunities. Here are a few examples of different levels of risk ordered from high to low. One, if you don't do this, competitors with AI can make you obsolete. If AI poses a major existential threat to your business, incorporating AI must have the highest priority. In the 2023 Gartner study, 7% cited business continuity as their reason for embracing AI. This is more common for businesses involving document processing and information aggregation, such as financial analysis, insurance, and data processing. This is also common for creative work such as advertising, web design, and image production. You can refer to the 2023 OpenAI study, GPTs are GPTs, to see how industries rank in their exposure to AI. So yeah, this is a very good point here. If let's say I've opened an AI company and I specialize in building agentic AI applications, one of the things I can pitch to companies is the existential threat that they face if they don't build AI applications. The fact that their competition will beat them to the race. most serious companies wouldn't want to be beaten. So if you pitch based on that, if you make them know, if you're lucky, they would even have known themselves. But if you're able to let them know why they need the AI applications that you build, especially the workflow applications, then I think you'll get a lot of companies signing up to your service. Two, if you don't do this, you will miss opportunities to boost profits and productivity. Most companies embrace AI for the opportunities it brings. AI can help in most, if not all, business operations. AI can make user acquisition cheaper by crafting more effective copyrights, product descriptions, and promotional visual content. AI can increase user retention by improving customer support and customizing user experience. AI can also help with sales lead generation, internal communication, market research, and competitor tracking. You are unsure where AI will fit into your business yet, but you don't want to be left behind. So that is the third point. While companies shouldn't chase every hype train, many have failed by waiting too long to take the leap. So like Kodak, Blockbuster, and BlackBerry. Investing resources into understanding how a new transformational technology can impact your business isn't a bad idea. If you can afford it, do it. At bigger companies, this can be part of the R&D department. Once you find a good reason to develop this use case, you might consider whether you have to build it yourself. If AI poses an essential threat to your business, you might want to do AI in-house instead of outsourcing it to a competitor. However, if you are using AI to boost profits and productivity, you might have plenty of buy options that can save you time and money while giving you better performance. The role of AI and humans in the application. Okay. Before we go on, I'm just gonna um I've got I've opened my window and I want to close it. So I'll be right back, guys, because it's getting colder here. Right, we are back. So let's continue. The role of AI and humans in the application. What role AI plays in the AI product influences the application's development and its requirements. Apple has a great document explaining different ways AI can be used in a product. Here are three key points relevant to the current discussion. One, critical or complementary. If an AI can still work, if an app can still work without AI, AI is complementary to the app. For example, Face ID wouldn't work without AI powered facial recognition, whereas Gmail will still work without Smart Compose. Okay, so this is a very good point. Um, is it critical or complementary? So before um, AI generative, uh, you know, the models before AI applications were deployed into Gmail, where it can help you to generate emails and all of that. We were using Gmails fine. We didn't really need that. So it's complementary to making Gmail work. But like he said, Face ID, it needs AI powered facial recognition. Okay, and that without that, it cannot work. So it's critical. Yeah. Then we have reactive or proactive. The reactive feature shows its responses in reaction to users' requests or specific actions, whereas a proactive feature shows its responses when there is an opportunity for it. For example, a chatbot is reactive, whereas traffic alerts on Google Maps are proactive. Because reactive features are generated in response to events, they usually, but not always, need to happen fast. On the other hand, proactive features can be pre-computed and shown opportunistically, so latency is less important. Because users don't ask for proactive features, they can view them as intrusive or annoying if the quality is low. Therefore, proactive predictions and generations typically have a higher quality bar. Okay, dynamic or static. Dynamic features are updated continually with user feedback, whereas static features are updated periodically. For example, Face ID needs to be updated as people's faces change over time. However, object detection in Google Photos is likely updated only when Google Photos is upgraded. In the case of AI, dynamic features might mean that each user has their own model continually fine-tuned on their data or other mechanisms for personalization, such as ChatGPT's memory feature, which allows ChatGPT to remember each user's preferences. However, static features might have one model for a group of users. If that's the case, these features are updated only when the shared model is updated. Okay, so another great point. It's also important to clarify the role of humans in the application. Will AI provide background support to humans, make decisions directly, or both? For example, for a customer support chatbot, AI responses can be used in different ways. AI shows several responses that human agents can reference to write faster responses. AI responds only to simple requests and routes more complex requests to humans. AI responds to all requests directly without human involvement. Involving humans in AI's decision-making process is called human in the loop. Microsoft 2023 proposed a framework for gradually increasing AI automation in products that they call crawl, walk, run. Crawl means human involvement is mandatory. Walk means AI can directly interact with internal employees. Run means increased automation, potentially including direct AI interactions with external users. The role of humans can change over time as the quality of the AI system improves. For example, in the beginning, when you are still evaluating AI capabilities, you might use it to generate suggestions for human agents. If the acceptance rate by human agents is high, for example, 95% of AI suggested responses to simple requests are used by human agents verbatim. You can let customers interact with AI directly for those simple requests. Okay, AI product defensibility. If you are selling AI applications as standalone products, it's important to consider their defensibility. The low entry barrier is both a blessing and a curse. If something is easy for you to build, it's also easy for your competitors. What moats do you have to defend your product? In a way, building applications on top of foundation models means providing a layer on top of these models. This also means that if the underlying models expand in capabilities, the layer you provide might be subsumed by the models, rendering your application obsolete. Imagine building a PDF parsing application on top of ChatGPT based on the assumption that ChatGPT can parse PDFs well or can do so at scale. Your ability to compete will weaken if this assumption is no longer true. However, even in this case, a PDF parsing application might still make sense if it's built on top of open source models, sharing your solution towards users who want to host models in-house. Yeah, this is a very good point because people were building all sort of applications on top of the GPT models. But sometimes, for example, an AI application that can talk to your PDF, ChatGPT can talk my PDF. So if I've already subscribed to ChatGPT Plus, I don't see why I should subscribe to your product when ChatGPT is doing a fantastic job. You just have to upload the PDF to ChatGPT and it can analyze it, it can talk to it, ask any question, and it can tell me. Okay, there used to be an AI application like that. It was free. Later, they wanted to people to pay. I never even bought it because I knew ChatGPT could do all of that. There was this AI application I signed up to. It generates images for like mockups and all of that. And it turns out that they built that application on top of a ChatGPT, on top of GPT model. And, you know, now you can generate those images straight away from ChatGPT. So that is a very good point. Yeah. One general partner at a major VC firm told me that she's seen many startups whose entire products could be a feature for Google Docs or Microsoft Office. If their products take off, what would stop Google or Microsoft from allocating 3 engineers to replicate these products in 2 weeks? In AI, there are generally 3 types of competitive advantages: technology, data, and distribution. The ability to bring your product in front of users. With foundation models, the core technologies of most companies will be similar. The distribution advantage likely belongs to big companies. The data advantage is more nuanced. Big companies likely have more existing data. However, if a startup can get to market first and gather sufficient user data to continually improve their products, data will be their moat. Even for the scenarios where user data can be used to train models directly, usage information can give invaluable insights into user behaviors and product shortcomings, which can be used to guide the data collection and training process. There have been many successful companies whose original products could have been features of larger products. Calendly would have been a feature of Google Calendar. MailChimp could have been a feature of Gmail. Photoroom could have been a feature of Google Photos. Many startups eventually overtake bigger competitors, starting by building a feature that these bigger competitors overlooked. Perhaps yours can be the next one. Okay, that's good to know. Setting expectations. Once you've decided that you need to build this amazing AI application by yourself, the next step is to figure out what success looks like. How will you measure success? The most important metric is how this will impact your business. For example, if it's a customer support chatbot, the business metrics can include the following. What percentage of customer messages do you want the chatbot to automate? How many more messages should the chatbot allow you to process? How much quicker can you respond using the chatbot? How much human labor can a chatbot save you? During the process of writing this book, I could hardly talk to any AI startup without hearing the phrase data flywheel. Okay, all right, interesting. A chatbot can answer more messages, but that doesn't mean it will make users happy. So it's important to track customer satisfaction and customer feedback in general. Okay, user feedback on page 474 discusses how to design a feedback system. To ensure your product isn't put in front of customers before it's ready, have clear expectations on its usefulness threshold. How good it has be, how good it has to be for you to be useful. Usefulness thresholds might include the following metrics groups: quality metrics to measure the quality of the chatbot's responses, latency metrics including TTFT time to first token, TPOT time per output token, and total latency. What is considered acceptable latency depends on your use case. If all of your customer requests are currently being processed by humans with a median response time of an hour, anything faster than this might be good enough. Cost metrics: how much it costs per inference request. Other metrics such as interpretability and fairness. If you're not yet sure what metrics you want to use, don't worry. The rest of the book will cover many of these metrics. Milestone planning. Once you've set measurable goals, you need to plan to achieve these goals. How to get to the goals depends on where you start. Evaluate existing models to understand their capabilities. The stronger the off-the-shelf models, the less work you will have to do. For example, if your goal is to automate 60% of customer support tickets, and the off-the-shelf model you want to use can already automate 30% of the tickets, the effort you need to put in might be less than if it can automate no tickets at all. It's likely that your goals will change after evaluation. For example, after evaluation, you may realize that the resources needed to get up to the usefulness threshold will be more than its potential return. And therefore, you no longer want to pursue it. Yeah, that's true. Applying an AI, hmm, some electrolyte to keep me hydrated. Planning an AI product needs to account for its last mile challenge. Initial success with foundation models can be misleading as the base capabilities of foundation models are already quite impressive. It might not take much time to build a fun demo. However, a good initial demo doesn't promise a good end product. It might take a weekend to build a demo, but months and even years to build a product. In the paper Ultra Chat, Think et al. Shared that the journey from 0 to 60 is easy, whereas progressing from 60 to 100 becomes exceedingly challenging. LinkedIn 2024 shared the same sentiment. It took them 1 month to achieve 80% of the experience they wanted. This initial success made them grossly underestimate how much time it would take them to improve the product. They found it took them 4 more months to finally surpass 95%. A lot of time was spent working on the product kinks and dealing with hallucinations. The slow speed of achieving each subsequent 1% gain was discouraging. Maintenance. Product planning doesn't stop at achieving its goals. You need to think about how this product might change over time and how it should be maintained. Maintenance of an AI product has the added challenge of AI's fast pace of change. The AI space has been moving incredibly fast in the last decade. It'll probably continue moving fast for the next decade. Building on top of foundation models today means committing to riding this bullet train. Many changes are good. For example, the limitations of many models are being addressed. Context lengths are getting longer. Model outputs are getting better. Model inference, the process of computing an output, giving an input, is getting faster and cheaper. Figure 111 shows the evolution of inference cost and model performance on massive multitask language understanding (MMLU). Okay, right. So these are all models: GP3 Da Vinci, GP3 Da Vinci, GP3 Curie, Mistral, Cohere. Love it, love it, love it, love it, love it. Okay. So, however, even these good changes can cause friction in your workflows. You'll have to constantly be on your guard and run a cost benefit analysis of each technology investment. The best option today might turn into the worst option tomorrow. You may decide to build a model in house because it seems cheaper than paying for model providers, only to find out after 3 months that the model that only to find out after 3 months that model providers have dropped their prices in half, making in-house the expensive option. You might invest in a third-party solution and tailor your infrastructure around it, only for the provider to go out of business after failing to secure funding. Some changes are easier to adapt to. For example, as model providers converge to the same API, it's becoming easier to swap one model API for another. However, as each model has its quirks, strengths, and weaknesses, developers working with the new model will need to adjust their workflows, prompts, and data to this new model. Without proper infrastructure for versioning and evaluation in place, the process can cause a lot of headaches. Some changes are harder to adapt to, especially those around regulation. Technologies surrounding AI are considered national security issues for many countries, meaning resources for AI, including compute, talent, and data, are heavily regulated. The introduction of Europe's General Data Protection Regulation (GDPR), for example, was estimated to cost businesses 9 billion USD to become compliant. Compute availability can change overnight as new laws put more restrictions on who can buy and sell compute resources. See the US October 2023 Executive Order. If your GPU vendor is suddenly banned from selling GPUs to your country, you are in trouble. Right. This is very interesting. Recently, I saw a tweet from some Altman CEO of OpenAI, the creators of ChatGPT. This guy was saying that they are partnering with, I think, Broadcom so that they build their own chips, AI chips. And I'm sure when NVIDIA hears of this, they'll be like, whoa, these guys, they are moving from software to hardware. Some is something else. I think it's one of the reasons why they fought for him to be in OpenAI when some of the founding fathers were trying to kick him out because that guy has got what it takes. He's daring. He was also talking about making ChatGPT appealing to adult use. That they are going to introduce by the end of the year a new model that will mean that there will be erotic. It can produce erotic content. So, for example, you can prompt the model to produce erotic images. And as long as you are able to confirm that you are 18 plus, you'll be able to do that. And when I look at the comments on the tweet, people were generally happy. So, yeah, some changes can be fatal. For example, regulations around intellectual property and AI usage are still evolving. If you build your product on top of a model trained using other people's data, can you be certain that your product's IP will always belong to you? Many IP-heavy companies I've talked to, such as game studios, hesitate to use AI for fear of losing their IPs later on. Once you've committed to building an AI product, let's look into the engineering stack needed to build these applications. The AI engineering stack. I think this is where my interest is, and this is where I will start putting some notes. The AI engineering. AI engineering stack. AI engineering's rapid growth also induced an incredible amount of hype and FOMO, fear of missing out. The number of new tools, techniques, models, and applications introduced every day can be overwhelming. Instead of trying to keep up with the constantly shifting sand, let's look into the fundamental building blocks of AI engineering. To understand AI engineering, it's important to recognize that AI engineering evolved out of ML engineering. When a company starts experimenting with foundation models, it's natural that its existing ML team should lead the effort. Some companies treat AI engineering the same as ML engineering, as shown in figure 112. Okay, senior machine learning engineer, generative AI, Robin Hood, New York, software engineer, AI systems. Wow, look at the amount. Staff plus machine learning engineer, generative AI, ML AI operations engineer. Machine learning engineer, large language models, and generative AI. Wow. AI ML staff, software engineer. Staff machine learning. Wow. Okay. Wow. Some companies have separate job descriptions for AI engineering as shown in figure 1.3. So if you scroll down, yeah, principal AI engineer, then senior generative AI software engineer, NVIDIA. AI engineer, generative AI engineer, generative AI senior, generative AI engineer, lead artificial intelligence AI engineer, AI engineer. Okay, so they separated from ML. Some put it together. Regardless of where organizations position AI engineers and ML engineers, their roles have significant overlap. Existing ML engineers can add AI engineering to their list of skills to expand their job prospects. However, there are also AI engineers with no previous ML experience. To best understand AI engineering, how it differs from traditional ML engineering, the following sections breaks down different layers of the AI application building process and looks at the role each layer plays in AI engineering and ML engineering. Okay, so let's dive in. 3 layers of the AI stack. There are 3 layers to any AI application stack: application development, model development, and infrastructure. Right, the AI engineering stack. So we got application development, then we have model development, then we have infrastructure. Right. Application development. What is it? With models readily available, anyone can use them to develop applications. This is the layer that has seen the most action in the last 2 years and is still rapidly evolving. Application development involves providing a model with good prompts and necessary context. This layer requires rigorous evaluation. Good applications also demand good interfaces. So, application development to providing model with the prompts are the prompt engineering and necessary context. Requires rigorous evaluation and requires good interfaces. Okay, model development. This layer provides tooling for developing models, including frameworks for modeling, training, fine-tuning, and inference optimization. Because data is central to model development, this layer also contains data set engineering. Model development also requires rigorous evaluation. Rigorous eval. So, model development provides tooling for developing models. So, provides tooling for developing models. So, this include frameworks for modeling, training, fine tuning, and inference optimization. So data is central to model development. So it also requires data engineering or data set engineering. Also requires rigorous eval. Rigorous eval. Infrastructure at the bottom is at the bottom is the stack is infrastructure. Okay, it should be at the bottom of the stack. At the bottom of the stack. So Chip, if you are watching, I've just seen something that you need to correct in your book. At the bottom of the stack is infrastructure, which includes tooling for model 7, managing data and compute and monitoring. Okay, so infrastructure is the bottom of the stack. And this includes includes tooling for model, managing data and compute, and monitoring. All right, so the three layers and examples of responsibilities for each layer are shown. So application development, we've got AI, interface, prompt engineering, context construction, evaluation, model development, inference optimization, dataset engineering, modeling and training, eval, infrastructure, compute management, data management, serving, monitoring. Yeah, so all right, I'm going to take a screenshot of this. Put it in my notes. Ooh. Okay, so I think I would do a LinkedIn post on this one. Chip. What's the name? Yeah, I'm trying to do a LinkedIn post on this thing. So Chip Huyen. So Chip Huyen. Author of AI engineering. Talks about the three layers of AI engineering. Okay, we will come back to it. All right. So these are the three layers of engineering, according to the author. To get a sense of how the landscape has evolved with foundation models, in March 2024, I set GitHub for all AI-related repositories with at least 500 stars. Given the prevalence of GitHub, I believe this data is a good proxy for understanding the ecosystem. In my analysis, I also included repositories for applications and models, which are the products of the application development and model development layers, respectively. I found a total of 920 repositories. Figure 121 shows the cumulative number of repository in each category month over month. Wow. The data shows a big jump in the number of AI toolings in 2023. After the introduction of Stable Diffusion and ChatGPT in 2023, the categories that saw the highest increases were applications and application development. The infrastructure layer saw some growth, but it was less than the growth seen in other layers. This is expected, even though models and applications have changed, the core infrastructure needs, resource management, serving, monitoring, etc., remain the same. This brings us to the next point. While the level of excitement and creativity around foundation models is unprecedented, many principles of building AI applications remain the same. For enterprise use cases, AI applications still need to solve business problems, and therefore it's still essential to map from business metrics to ML metrics and vice versa. You still need to do systematic experimentation. With classical ML engineering, you experiment with different hyperparameters. With foundation models, you experiment with different models, prompts, retrieval algorithms, sampling variables, and more. Sampling variables are discussed in chapter 2. You still want to make models run faster and cheaper. It's still important to set up a feedback loop so that we can iteratively improve our applications with production data. This means that much of what ML engineers have learned and shared over the last decade is still applicable. This collective experience makes it easier for everyone to begin building AI applications. However, built on top of these enduring principles are many innovations unique to AI engineering, which we will explore in this book. AI engineering versus ML engineering. While the unchanging principles of deploying AI applications are reassuring, it's also important to understand how things have changed. This is helpful for teams that want to adapt their existing platforms for new AI use cases and developers who are interested in which skills to learn to stay competitive in a new market. At a higher level, building applications using foundation models today differs from traditional ML engineering in three major ways. One, without foundation models, you have to train your own models for your applications. With AI engineering, you use a model someone else has trained for you. This means that AI engineering focuses less on modeling and training and more on model adaptation. AI engineering works with models that are bigger, consume more compute resources, and incur higher latency than traditional ML engineering. This means that there is more pressure for efficient training and inference optimization. A corollary of compute intensive models is that many companies now need more GPUs and work with bigger compute clusters than they previously did, which means there is more need for engineers who know how to work with GPUs and big clusters. AI engineering works with models that can produce open-ended outputs. Open-ended outputs give models the flexibility to be used for more tasks, but they are also harder to evaluate. This makes evaluation a much bigger problem in AI engineering. In short, AI engineering differs from ML engineering in that it's less about model development and more about adapting and evaluating models. I've mentioned model adaptation several times in this chapter. So before we move on, I want to make sure that we're on the same page about what model adaptation means. In general, model adaptation techniques can be divided into two categories depending on whether they require updating model weights. Prompt-based techniques, which include prompt engineering, adapt a model without updating the model weight. You adapt a model by giving it instructions and context instead of changing the model itself. Prompt engineering is easier to get started and requires less data. Many successful applications have been built with just prompt engineering. It's easy. Its ease of use allows you to experiment with more models, which increase your chance of finding a model that is unexpectedly good for your applications. However, prompt engineering might not be enough for complex tasks or applications with strict performance requirements. Fine-tuning, on the other hand, requires updating model weights. Adapt a model by making changes to the model itself. In general, fine-tuning techniques are more complicated and require more data, but they can improve your model's quality, latency, and cost significantly. Many things aren't possible without changing model weights, such as adapting the model to a new task it wasn't exposed to during training. Now let's zoom in into the application development and model development layers to see how it has changed with AI engineering, starting with what existing ML engineers are more familiar with. This section gives an overview of different processes involved in developing an AI application. How these processes work will be discussed throughout this book. Okay, model development is the layer most commonly associated with traditional ML engineering. It has three main responsibilities: modeling and training, data set engineering, and inference optimization. Evaluation is also required, but most people will come across it first in the application development layer. I'll discuss evaluation in the next session. Modeling and training. Modeling and training refers to the process of coming up with a model architecture, training it, and fine-tuning it. Examples of tools in this category are Google's TensorFlow, Hugging Faces, Transformers, and Meta's PyTorch. Developing ML models requires specialized ML knowledge. It requires knowing different types of ML algorithms such as clustering, logistic regression, decision trees, and collaborative filtering, and neural network architecture such as feed forward, recurrent, convolutional, and transformer. It also requires understanding how a model learns, including concepts such as gradient descent, loss function, regularization, etc. With the availability of foundation models, ML knowledge is no longer a must-have for building AI applications. I've met many wonderful and successful AI application builders who aren't at all interested in learning about gradient descent. However, ML knowledge is still extremely valuable as it expands the set of tools that you can use and helps troubleshooting when a model doesn't work as expected. Okay. The differences among training, pre-training, fine-tuning, and post. Okay, so I'm going to end here because I just want to do an hour today and prepare for work. So yeah, it's been great today. The major thing we are looking at is the AI engineering stack. And we've talked about the three stacks: application development, model development, and infrastructure. And it looks like when we talk about machine learning, it's mostly about the model development, and application development is building on the model. You could use prompt engineering or you could use fine-tuning. Fine-tuning involves changing the weights, making changes to the weights of the model. And prompt engineering is just prompt engineering, using good prompts and context construction to speak to the model and make the model do the work. Some people do what they call jailbreaking. Sometimes somebody's asked me a question on one of my videos that how do you jailbreak ChatGPT? And I asked him why do you want to do that? If he's talking about changing the weights of the model, then it's fine. But if he's talking about using some intelligent yet illegal in code, because who defines the rules? Illegal way of making ChatGPT do something that the model has not been trained to do, then I wouldn't want to help him to do that. So yeah, we'll end here, guys. Thank you for today, and yeah, I will see you in the next video. Bye for now.